Let's start by looking at the difference between equations and expressions. An equation. An equation is something that contains an equal sign. So if you have some sort of mathematical expression, I hate to use that word because we'll use it for something else, but some sort of mathematical statement, and that statement has an equal sign in it, then you're talking about an equation, something on the left equal exactly the same as something on the right. E equals mc squared is a very famous equation. It's Einstein's formula relating mass and energy. The energy is equal to the mass times the speed of light squared. An expression. That's a mathematical relationship without an equal sign. For example, 9c divided by 5 minus 32 is an expression because there's no equal sign in it. And this happens to be the Fahrenheit temperature in terms of Celsius or centigrade. Numeric expressions are only made up of numbers. For example, there's a numeric expression, and as we've seen in the previous classes and units, we can actually do the math and evaluate this expression. If I were to work this through, I would find out that it's equal to minus 25. Algebraic expressions, on the other hand, contain variables, and unless you know the values for those variables, there's no way to get a single number that describes it. 3x squared minus 2xy plus 4y squared is an algebraic expression, and unless someone tells you what x and y is, you have to leave it like that. You can't go any further. Let's see how you can do determining whether something is an equation or an expression. V is equal to LWH. You might recognize this as the volume is equal to the length, the width times the height. Is that an expression by our definition or an equation? Equation because there's the equal sign. C plus 273. Expression, there's no equal sign, it's just a mathematical statement with two terms in it. 5 times the quantity f minus 32 over 9. That also is an expression because there's no equal sign. Here's something very similar. C equals 5 times the quantity f minus 32 divided by 9. That's an equation because of the equal sign. As we said, if you have expressions and you're given an expression, it can be evaluated if you're given some additional information. In other words, I could take 5 times the quantity f minus 32 divided by 9 and determine what that ultimately is equal to if someone were to tell me what f is. So how can I go from here to find the value of the expression? Let's look at a rule. To evaluate an expression, we substitute the given value for the appropriate variable and then do the math. Let's try it with this one. 5 times f minus 32 divided by 9, where f is 50. So what I do is I plug the 50 where I had f. Now I have a purely numeric expression, and I can continue to evaluate it numerically. The first thing I'll do, as we've learned before, is operate on what's inside the parentheses. 50 minus 32 is 18, so I have 5 times 18 divided by 9. 5 times 18 is 90 divided by 9, so I've evaluated this expression as 10 when f is equal to 50. Let's try another one that might be a tiny bit more interesting. This one, you see, has two variables, x and y, and we're going to try to evaluate this when x is equal to 3 and y is equal to minus 2. As we indicated before, where we had an x, we'll put in the 3, and where we have a y, we'll put in the minus 2, and then we'll continue to evaluate it using the rules we've learned when we looked at evaluating expressions and the order of operations. We can work on these 2 by 2 in a way. Let's solve 3 squared. We'll solve 3 times minus 2 and minus 2 squared. So we then get 3 times 9 plus 2 times minus 6 plus 5 times 4. We can calculate each one of those 3 things and get 27 plus minus 12 plus 20. We can evaluate this to find 35. I might stop here for a second and just talk about quick ways of doing math. When I look at that, I see 27 minus 12 plus 20. That is a little bit difficult to do in your head, but there are a few tricks, and I just thought I'd stop here for a second to show you a trick that I use in evaluating something like this. Let's take a look at that expression again. First of all, I know that I don't have to add things in order. So I see 27 and 20, and I know I can do that right away and get 47. Then I see minus 12, and I remember that minus 12 is minus 10 minus 2. So if I have 47 and take away 10, I get 37, and then take away 2, I get 35. So by breaking that minus 12 up into a minus 10 and a minus 2, I'm able to do this in my head rather quickly. So when you have to add columns of numbers, a good trick is to look around through the columns and see what you can add together easily or what you can split apart to make the addition simpler. Sorry for the little side trip, but sometimes side trips are interesting, and I thought I'd just share that with you since this seemed like an appropriate place to do it. Let's go on. Here's another expression that we can evaluate. It's a little bit more complicated. We're going to use x equal to 4 and y equal to 6. As we did before, we substitute those values, 4 and 6, into the appropriate parts of the equation. Then the next thing I'm going to do is perform the square operations because I need to take care of those exponents to the powers. 4 squared will be 16, 6 squared will be 36, and I will get this expression. I can work this out and get 52 over 26 minus 26. You have to be careful. So I'm dividing a positive by a negative, so when I'm finished, I get minus 2. Now, this looks very, very complicated, but we're going to try to evaluate this for r equal to 10 and s equal to 4. Just as we did before, I'm going to substitute those values, 10 for r and 4 for s. So I have 4 times the square root of 10 squared minus 4 squared minus 3 over 10 squared plus 4 squared plus 28. I can do the math. First, I've done the squares. Now, before I can do anything under that square root, I need to combine that expression so that I have one number, because the square root of each individual number added or subtracted is not the same as the square root of the sum or difference represented there. So I need to do the math. When I do, I get 4 times 81, the square root of 81, divided by the square root of 144. The square root of 81 is 9. The square root of 144 is 12. So now my expression becomes 4 times 9 divided by 12. That's equal to 36 divided by 12, which gives me 3. Going to switch topics a little bit, and we're going to talk about monomials and polynomials. And I couldn't resist. Hi, my name is Polly. Guess what her last name is? At any rate, let's go on and look at some of the vocabulary we're going to need to deal with complicated mathematical expressions strung together by pluses and minuses. Let's go on. A monomial is a single term where you've multiplied everything together. It consists of numbers, constants like the 5, and variables all multiplied together. And remember, the operant word is multiplied. When you have a monomial in a big row of other things, for example, dot, 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 who knows what comes in front of it, plus 5x squared y plus dot, 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 that's called a term in a larger string of mathematical notation. Constants and variables within a monomial can be raised to a power. For example, we see that we have x to the second power, and there are some things you will not find in a monomial. One is plus or minus. A monomial has to be things that are multiplied together, and you also won't find division in a monomial. In other words, everything must be multiplied. There can't be any division symbols, or it can't be one expression over another expression. It's just something like what we have here, 5x squared y, and that's all. Now, a polynomial is an expression made up of monomials added together. And remember, by saying added, we could also say adding the, we could have a minus sign, in which case we're adding the opposite if we're dealing with that on the number line. Now, a polynomial is an expression made up of monomials added together. Let's look at one. That's a polynomial. You see that there are many monomials or many terms in it, in fact 5, and the whole thing is a polynomial, and it's made up of monomials strung together with pluses or minuses. We can also say that each one of those monomials is a term in the polynomial. So you'll hear that vocabulary used as well. Be careful here. You might see something like this. And as I said before, 5x squared divided by y is not a monomial, because we're only dealing with multiplications, not divisions. A variable is divided, not multiplied here. It's not a monomial. Another quick quiz for you. Which of these are monomials? How about 10x cubed y squared z? Pretty complicated looking. Is that a monomial or not? Yes, it is, because there's just one term with everything only multiplied together. How about 5? Sure, it's a monomial, pretty simple one, because it doesn't violate any of those rules that we talked about that would keep us from calling it a monomial. There's nothing added or subtracted or divided. How about x squared plus y squared? Yeah, I almost goofed. No, that's not a monomial. Why isn't it? Because we have a plus, x squared plus y squared. It's actually a polynomial. There are several terms in there because the plus is in there. So it's definitely not. I got hooked into saying yes, 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 and almost made a mistake. I hope you didn't. How about xy divided by 2z? No, that's not, because in this case we have a division. So let's summarize. We have a monomial, and a monomial has a single term. If we don't have too many terms in our polynomial, we have some special names for them. A polynomial with 2 terms is called a binomial, just like a cycle with 2 wheels is a bicycle. Stretching it, huh? 2 terms, binomial, think of bicycle. 3 terms, trinomial, bring out my tricycle. Again, 3 terms is a trinomial. And a polynomial, it's like you can count to 3 in math. You have a monomial, a binomial, a trinomial, but when you hit 4 terms, you don't have a quadrinomial. Anything 4 or better is a polynomial. In fact, anything with 2 terms or better is a polynomial, although with 2 or 3 terms, we often use binomial or trinomial just to specify it. But literally, anything with greater than 1 term can be called a polynomial. Binomials and trinomials are also polynomials, but they're special cases, just like a rectangle can be considered a special case of a parallelogram, or a square is a special case of a rectangle. So that binomials and trinomials are also polynomials. Another little quiz. Which of these what are the following called? That's a binomial, 2 terms. Next one, polynomial, because it has 4 terms actually, so we can't say it's a monomial, binomial, trinomial. Here's something with 3 terms. Trinomial, 1 term. Monomial. Be careful here, it's a little bit of a trick. What's that top one called? You might think polynomial, but look at this. I have an x cubed and a 2x cubed. Since both of those are x cubes, and we'll look at this in quite a bit of detail later on in this class, I can add those 2 together and get 3x cubed plus 4x squared minus 4. So in reality, once I've combined those 2, which I can do and should do, what I have is a trinomial. Here's another trick one. That should give you a big hint. I have 3x squared and 2x squared. Since I have x squared in both cases, I can add them together to get 5x squared, and that makes that a monomial. Next, let's look at some of the vocabulary that we use dealing with monomials and polynomials. Actually, we look at the x raised to a power, and when we're looking at specifying monomials or polynomials, we call the power that any term within a monomial or polynomial is raised to the degree. In this case, we have a monomial of degree 2 because that x is raised to the 2nd power. We have a number multiplied in front of it. That number has another name. That number is called the coefficient. The numeral, the actual number that multiplies a term, is the coefficient. In this case, the coefficient is equal to -5. We can talk about the degree of a monomial that's a little more complicated. Here we have minus x squared y cubed. What's the degree of that? Here we have a square, here we have a cube. But they're 2 different variables, so what do we do to describe the degree? We add them. And so when you have a monomial made up of separate variables, each raised to a different power, we specify the degree of the monomial by adding the powers on each of those terms. So here we have the case 2 plus 3 is equal to 5. Here's a rule. To find the degree of any monomial expression, we add the powers of each of the variables of the monomial, just as we did in the previous example. Let's talk about the coefficient of this monomial. We have minus x squared y cubed. Now, you might say, well, it doesn't have a coefficient, but in a sense it does. We can just as easily put a 1 multiplying the x squared y cubed. It doesn't change the value. So if you see a monomial with a minus sign in front of it, you can think that they're really talking about a -1 there, and so that we can say that has a coefficient of -1. Notice also that when you're dealing with monomials, the coefficient includes the sign. So if you see -5 x squared y cubed, -5 is the coefficient, not just 5. Another rule: to find the coefficient of a monomial expression, we use the numerical value of the single term. Here's another example, 3z. The coefficient is z. And anything by itself where you don't see it raised to a power with an exponent automatically assumes it's 1. Therefore, 3z has a coefficient of 3 and a degree 1. Let's look at another example. We have minus 3 x to the 4th y squared z. First, let's pick out the coefficient. The coefficient is minus 3. Now let's look at the degree. We see that we have z without any power written after it. We have to remember that that's equal to 1. So the degree is 4 from the x, 2 from the y, and 1 from the z. So we say that's degree 6. The coefficient of 8. What's the coefficient? What's the degree if we just have a plain number? In order to talk about this, I'm going to take a little side trip. I think there was a play I saw once that said something like, sometimes you have to go a long way to go a short way correctly. So let's do that. We want to know what the coefficient and degree of just a plain number, if we saw it in a polynomial expression, would be. Let's try looking at how powers work. 2 to the 5th is 2 5 times, multiplied by itself 5 times, it's 32. 2 to the 4th is 16. 2 cubed is 8. 2 times 2 times 2. 2 squared is 4. 2 to the 1st power is 2. And here's where we're introducing something new. If you have something to the 0th power that's equal to 1, we can accept that now as a definition, and we'll be looking into the y of it in units to come. But we can make the general rule that any number raised to the 0th power is equal to 1. And I have to add here that 0 is excluded. A cannot be equal to 0. But any number other than 0 raised to the 0th power is equal to 1. There's our little side trip. We needed to know that if you took x to the 0th power, it's equal to 1. If you took y to the 0th power, it's equal to 1. If you took 3 million to the 0th power, it's equal to 1. Any number raised to the 0th power is 1. Remembering that, let's go back and look at our little 8. We can write plus 8 as 8x to the 0th power. And when you look at it this way, you should be able to see exactly what the coefficient is. It's 8. And what the degree is. It's 0. So if you have just a number, you can add or multiply whatever variable you would like to it, raise it to the 0th power. So a number has degree 0 and the coefficient is just the number. Now let's look at like terms. Like terms are monomials with the same variables raised to the same exponents. For example, the coefficients could be different. Let's see if we look in this example to identify the like terms. Which ones are the same? Well, we have minus 8x cubed y and a 32 x cubed y. In both cases, we have x to the 3rd power, y to the 1st power, and nothing else. That's a like term. How about a quick quiz? Which are like terms? How about 3xy and 8x squared y? Is that a like term or not? No, it's not. How about 13x cubed y squared and 14y squared x cubed? Be careful here. Those look different, but yes, that's a like. Those two are like terms. Remember, with multiplication, you can swap the order around and not change anything. But in both cases there, they have the same variables raised to the same powers. 47 and 18x. No. What about minus 10x cubed y squared z and 8zy squared x cubed? Again, be careful here. Check the x's, they're both cubed. Check the y's, they're both squared. Check the z, it's both to the 1st power. So this would be a yes. let's identify and combine these like terms. First of all, we have 3y cubed and 5y cubed. We can put those together. That's 8y cubed. Then there's no other y squareds. We bring that down. There are no other y's. We just bring that down. And there are no other units, so we can just bring that down. So that's as much as we've been able to combine.